the photoelectric effect. This is the observation, right? The observation that led to Einstein's idea that light is made up of particles. In other words, what we think of as photons, right? So, and it also gives a reason for Planck's need to have light be quantized, right? To explain the ultraviolet catastrophe and remove the infinite energies issue and all that stuff. So, the photoelectric effect, right? So it turns out Einstein, people knew this, right? Einstein studied it further and realized some things, but light shining on metal can cause electrons to be ejected, all right? So, it turns out that the details of how the electrons are ejected can't be explained with wave properties of light. So, yeah, Einstein's evidence that light is quantized and it can only carry specific minimum quantities of energy, and then that's eventually the conclusion that light's actually particles, and that's why that is, right? So again, our goal is to have a really good understanding of why this photoelectric effect phenomenon can't be explained by wave properties, right? And that it can only be explained by light being made up of particles, right? So at this stage, we're going to certainly focus a ton on the concepts rather than jumping right to the mathematical calculations. There is one question in the homework that's a mathematical calculation, but I mean it's not the main focus. Okay. So you'll see as we go here. So this right now is a demo of the photoelectric effect. So I'll just let this go here. I'm going to turn volume off here. It's music soundtrack. So they charge these tinsel strips up, as you can see, static electric charge built up there, and they charge by contact and get charged up, right? And at the beginning of the video, the person touched it and grounded it out, right? So the charge disappeared. Now, instead of grounding it out, they're going to put light on there, UV light. So they're going to shine UV light on, there we go. So when they shine UV light on the metal, some electrons get ejected off, and so basically it's going to lose a bunch of electrons. So presumably this was negatively charged, right? And so let's just see the effect here. There's the UV light, and you can see it just slowly ejecting electrons off. So it's just another way of getting rid of those excess electrons, right? So that's that's noticed, right, by scientists, and then they look into it as to what's going on. And Einstein looked into it and realized that it led to his prediction that light was made up of particles, right? So yeah, so let's get going here. So this is just another video of the same thing. It's just a little more scientific. Well, I don't know, it's not really more scientific, but it's just a different style of electroscope and so on, but same thing. Charge up the electroscope, shine the UV light, and the charge goes away. Okay, so you can check out the link if you want. So the reason wave theory can't explain this phenomenon is subtle, and it's in the details, all right? So wave theory indicates that electromagnetic radiation needs to come in minimum size lumps of energy, right? We know this in order to avoid predictions that black bodies emit thermal energy in an infinite amount. And yeah, but there was no reason given for these lumps or minimum amounts possible. So it was used because it was such a good model. It predicted things, but there was no fundamental reason for it, which bothered a lot of people, of course, right? So it bothered Einstein. Einstein was the type to Einstein was the type to question these things, right? He wasn't just going to, go along with things and just not look into it further. That was the big part of his genius, right? So more bits from a book here for us that helps justify the details of why it indicates that light is really made up of particles, right? So Planck had no justification for his pivotal introduction of lumpy energy. Oh my goodness. Sorry guys, keep having to pause there because of announcements. Anyway, so there's no compelling reason for why the energy has to come in these individual packets, right? So as the physicist George Gamow once said, it's as if nature allowed blah, blah, blah. I've already told you that one, I think, actually. So Einstein came up with his explanation by puzzling over something known as the photoelectric effect. The German physicist Heinrich Hertz, from the frequency units, right, Hertz, in 1887 was the first to find that when electromagnetic radiation, i.e. light is one of the examples, shines on certain metals, they emit electrons. By itself, this is not particularly remarkable. Metals have the property that some of their electrons are only loosely bound within atoms, which is why they're such good conductors of electricity. When light strikes a metallic surface, it relinquishes energy, it gives energy to the surface, much as it does when it strikes the surface of your skin, causing you to feel warmer on a sunny day, right? So this transferred energy can agitate electrons in the metal, and some of the loosely bound electrons can get knocked clear off the surface. Okay? But the strange features of the photoelectric effect become apparent when one studies more detailed properties of the ejected electrons. At first sight, you would think that as the intensity of the light, its brightness, is increased, the speed of the ejected electrons would also increase, since the impinging electromagnetic wave has more energy. Sorry, that was the end of the sentence. But this does not happen, right? Rather, the number of ejected electrons increases, but their speed stays the same. On the other hand, it has been experimentally observed that the speed of the ejected electrons does increase if the frequency of the impinging light is increased. And equivalently, their speed decreases if the frequency of the light is decreased. For electromagnetic waves in the visible part of the spectrum, an increase in frequency corresponds to a change in color from the red to the orange to the yellow to the green to the blue to the, and so on, finally violet. Frequencies higher than violet are not visible and correspond to ultraviolet, and subsequently after that, X-rays, and so on, right? Frequencies lower than that are also not visible in infrared, and it goes down to microwave and radio waves, and so on. That's the complete electromagnetic spectrum that we're talking about. So, in fact, as the frequency of light used is decreased, there comes a point when the speed of the emitted electrons drops to zero and they stop being ejected from the surface. And here's the weird part: regardless of the possible blinding intensity of the light source. For some unknown reason, the color of the impinging light beam, not its total energy, controls whether or not electrons are ejected. Total energy being the key there, right? And if they are ejected, the energy that they have. So there's this big link to the frequency. To understand how Einstein explained these puzzling facts, let's go back to the creepy warehouse, which has now been heated up to that 80 degrees. Imagine that the landlord, who hates children, requires everyone under the age of 15 to live in the sunken basement of the warehouse. It gets dark. Which the adults can view from a huge wraparound balcony. Moreover, the only way any of the enormous number of basement-bound children can leave the warehouse is if they can pay the guard an 85-cent exit fee. This landlord is such an ogre, it says. The adults who, at your urging, the children are the electrons in the atoms, right? Held in the atoms, like being held in the basement or whatever. The adults who, at your urging, have arranged the collective wealth by denomination, as described previously, can give money to the children only by throwing it down to them from the balcony, and let's see what happens. So the person carrying pennies begins tossing a few down, but this is far too meager of a sum for any children to be able to afford the departure fee. And because there's essentially an infinite sea of children all ferociously fighting for the falling money, even if the penny entrusted adult throws down enormous numbers down, no individual child will ever come anywhere near collecting 85 cents that he or she needs to pay the guard, right? So the same is true for the adults carrying nickels, dimes, quarters, and so on. Although each can toss down a staggeringly large amount of money, this is the intensely bright light, right? If any single child is lucky, he or she is only going to get a coin. Most are going to get nothing at all because you're throwing money down at an infinite sea of children, right? And certainly no child collects 85 cents necessary to leave. But then when the adult carrying dollars starts throwing them down, even in comparatively tiny sums, literally $1 by $1, right? Those lucky children who catch a single bill are able to leave immediately. Notice, though, that even though this adult loosens up and throws down barrels and barrels of dollar bills, they're like encouraged, like, yeah, let's do this, right? The number of children who are able to leave increases enormously, but each has exactly the same 15 cents left over after paying the guard, right? This is true regardless of the number of dollars tossed down. So the analogy here is going to be giving energy to the electrons. And so if you give them a little bit more energy than they need, they get ejected. And then the extra energy they have, they're going to carry away as the speed. Okay? And as you know from the past, the energy of individual photons is that proportionality, right? It's proportional to the frequency. So here's what this has to do with the photoelectric effect. Based on the experimental data reviewed above, Einstein suggested incorporating Planck's lumpy picture of wave energy into a new description of light. So Planck was all over the idea of the lumpy nature of energy, and then this is now saying, hey, light does that too, right? So the light beam, according to Einstein, should exactly be thought of as a stream of tiny packets, tiny particles of light, which were ultimately christened the name photons by chemist Gilbert Lewis. An idea we made use of in our, to get a sense of scale, according to his particle view of light, a typical 100-watt light bulb emits about 100 billion, that's 10 to the 20 photons per second. Einstein used this new conception to suggest a microscopic mechanism underlying the photoelectric effect. An electron is kicked off of a metallic surface, he proposed, if it gets hit by a sufficiently energetic photon. And what determines the energy of the individual photon? To explain his experimental data, Einstein followed Planck's lead and proposed the energy of each photon is proportional to the frequency of the light wave, with the proportionality factor being that of the Planck's constant. Now, like the children's minimum departure fee, the electrons in the metal must be jostled by a photon possessing a certain minimum energy in order to be kicked off the surface. As with the children fighting for the money, it's extremely unlikely that any one electron is going to get hit by more than one photon. Most don't get hit at all. But if the impinging light beam's frequency is too low, its individual photons will lack the punch necessary to eject the electrons. Just as no children can afford to leave regardless of the huge total number of coins the adult showers upon them, no electrons are jostled free, regardless of the huge total energy embodied in the impinging light beam, if its frequency and thus the energy of the individual photons is too low. But just as children are able to leave the warehouse as soon as the monetary denomination showered upon them gets large enough, electrons will be knocked off the surface as soon as the frequency of light shone on them, its energy denomination essentially, gets high enough. Moreover, just as the dollar-adjusted adult increases the total money thrown down, by increasing the number of, oh my god, woof. Right, so total intensity of light beam chosen, the frequency is increased by increasing the number of photons it contains, right? So, and just as more dollars resulted in more children being able to leave, more photons result in more electrons being hit and knocked off the surface. But notice that the leftover energy that each of these would have after ripping free from the atom depends solely on the energy of the photon that hits it, and that's determined by the frequency of the light beam, not its total intensity, right? So just as children leave the basement with 15 cents, no matter how many dollar bills are thrown down, each electron leaves the surface with with the same energy and hence the same speed, regardless of the total intensity of the impinging light beam. More total money simply means more children can leave, and more total energy means more electrons are not free. If we want the children to leave the basement with more money, we must increase the monetary denomination, and for electrons, we have to increase the frequency, right? So each photon has greater energy. This is precisely in accord with the experimental data. The frequency of the light, its color, determines the speed of the ejected electrons. The total intensity of light determines the number of ejected electrons. So Einstein showed that Planck's guess of lumpy energy actually reflects a fundamental feature of electromagnetic waves. They are composed of particles, photons, that are little bundles or quanta, if you call it that, of light. The lumpiness of the energy embodied by such waves is due to their being composed of particles. Einstein's insight represented great progress, but as we shall now see, the story is not as tidy as it might appear. Foreshadowing. Okay, we're going to get to that stuff later. So yeah, the photoelectric effect and the details about the energy and the electrons, how they're ejected and so on, depending on the frequency of light, can only be explained by light consisting of particles, right? An electron is ejected if and only if the light particle or the lump or the minimum quanta or whatever you want to call it, right, hits, if the one that hits it has enough energy, which Planck demonstrated and Einstein confirmed, right, depends on the frequency. So a wave could continuously add energy to an atom, just keep waving it, keep contributing energy until it finally gets enough and ejects an electron. That doesn't happen. So wave theory not working. Right, a particle of light can only hit once and give energy to that one atom, right? So that's the way it goes. If the frequency is too low, particles of light don't have enough energy to eject an electron, therefore no electrons emitted. Frequency of light's high enough. As soon as you get to a high enough frequency, all of a sudden particles start coming off, even if it's just a really dim light source. And then the electrons carry away the excess energy as kinetic energy. All this stuff is super calculatable, measurable, confirmable, right? So there's no denying the logic of this once Einstein put it all together. So here's a visual of this. You got light coming in, 700 nanometer light, which corresponds to 1.77 electron volt energy light packets. And so this little wave packet or particle, really, you could draw it as, right, hits, and electrons get, in this case, electrons don't get ejected. That's because 1.77 electron volts of energy is less than the 2 electron volts of energy needed to eject photons, right? Particles of light coming in don't have enough energy. And so even if you send, tons and tons and tons of this light, super bright, the metal might start to melt before any electrons get given off. Next one here, so more energy. So now it's got 2.25 electron volts. So it's got 0.25 to spare, right? So this energy that it goes off with, this velocity, this kinetic energy that it goes off with, corresponds to that 0.25. It's quite a simple idea, right? You've got the energy of the photon. Well, the energy the photon has is made up of the energy needed to eject the electrons and the kinetic energy of the electron, right? So energy, the photon comes in with 2.25. You need 2 to kick it out of the atom, and so kinetic energy you're left with is 0.25. Okay. I'll talk about the electron volt stuff in this slide here. Okay, so we're going to convert that 0.25 electron volts to joules. And I talked yesterday about how I'm going to show this in a little more detail. So here it is. The biggest thing that should be obvious to you is that 1 electron volt means 1 joule per coulomb. It's what a volt is defined as, right? So an electron volt means, that's 1 joule per coulomb. And so that breaks down to a certain amount of energy per electron. And so, since there's 1 coulomb of electrons is this many, if we divide that thing into that many pieces, right? If we divide, let me just undo that. If we divide this energy into, all those pieces, then we end up with this amount of joules, right? So really we have this either whichever conversion you're using, but 1 electron volt equals this many joules is my preference at this point for looking at that. And so then you say, well, 0.25 electron volts corresponds to how many joules? And of course, you have to look on this side. You want to know what to multiply by here to get the answer. So you look here to see what the multiple is. And it's always just second divided by first. All right. So you do that multiplication, the 0.25 times that 1.602, and you get 4.00, 10 to the negative 20, and that's the amount of joules. And then after that, you're going to convert to speed, right, or velocity, whichever you want to think of it. You have direction, so you're going to have the energy in there, and you're just going to multiply both sides by 2, and the mass is 9.11 times 10 to the negative 31 for electrons, so you divide that out. So you're multiplying both sides by 2 and dividing both sides by the mass of the electron, and getting 2.96 times 10 to the 5 meters per second. Okay, so this is the kind of math that when I saw this originally, that's kind of all we did. We looked at, the electron comes in, the photon comes in with energy, and then the electrons go off. But the significance of it was lost on me for sure. So conversion process based on understanding about, volts, meaning energy per charge, is my preference for sure. You can, of course, just, Google, conversion from electron volts to joules and type in 0.25 and it'll spit out the answer. But I mean, understanding, right, is sometimes underrated. The more you go into this, it's less about just getting the right answer in a high school course. It's about understanding the world around you is what we're doing this for, right? So here's another example, example 3. This one, you're going to confirm that speed, your practice assignment. Okay, so this one comes in with 2 electron volts, and again, it needs, it comes in with 3.1 electron volts, and it needs 2 to get ejected. So calculate what that speed would be based on the process we carried out. And again, you'll have that in the homework assignment or practice assignment, whatever you want to call it. And the solution's in the file afterwards that you can see after you've submitted. Okay, so make sure to go and look over solutions always, right? I think that's obvious. So you get good feedback about how you're doing. So the following is a great little applet. Yeah, there's a little applet here is going to show this. So I'll just review that. You can read it later, but I'm just going to load the little simulation here. So you have light shining on this shining on this surface and ejecting electrons, right? So it says, what do I have to do here? So I turned the intensity up. Right now, it was started out as off, right? So it wasn't doing anything. But I put more and more and more energy into the source here. This total amount of energy is as much as we can possibly blast at this thing, possibly melting the surface. It's so hot, things are smoking. No electrons though, no current flowing, right? So electrons would eject off, get attracted to this plate, go through, and you see current flowing. So we turn the intensity, well, actually leave it at any intensity you want or whatever, nothing going on. And then you'll find that eventually if you get to a frequency where the individual photons arriving are energetic enough, you'll actually get electrons ejected, right? So even if you had like super not very intense light shining on there, once in a while, there's going to be an electron ejected. I'm not sure how long I have to wait for a 5% intensity, but there you go, right? And obviously more intensity is just going to mean more of them, all with the same speed though. So I don't know what we have going on here. One faster than others. I'm confused about the applet, what it's doing there. But anyways, once you go to higher and higher UV, you're going to see more and more of them coming off faster and faster. Right? Anyways, some variation there. I'm not sure why. So hopefully that makes sense. So the summary: what is the frequency of light? Why does the frequency of light determine if the electrons are ejected and the resulting speed rather than the overall intensity? Well, Einstein said light is particles. Light arrives as particles. That'll come into play later on, but I mean, it's photons, right? So, and they carry a certain amount of energy that's proportional to the frequency, and so the photons have to have enough energy to eject the electrons, right? Since one photon contributes energy to one electron or one atom, the electron will only be ejected if that photon has enough energy, right? A wave could continuously add energy and build up over time and eject things eventually, but that is not observed to happen, right? If there is extra energy, of course, it goes out as speed, as kinetic energy, right? So, yeah, so like I said, even with extremely intense light, there wouldn't be any electrons ejected, which was quite surprising. Not what was expected, right? So there are big consequences to this. If light really is particles, right, then how can there be interference patterns as a wave property? And there's even more strangeness to come. So we'll get to all that stuff. Oh yeah, I want to do this for sure. So I'm gonna click on this one. No, that one doesn't work anymore. Fabric of the Cosmos. Still need pause. I'll get it loaded. All right, so this is part of a NOVA or presentation that was on PBS, I think it was. You can Google it. It's called The Fabric of the Cosmos, and it's Brian Greene, the author of the book. One of the books. I think it was the book we read from. Anyways, I'm just going to play it here. I'm going to turn my mic off so that you can hear just the computer audio. And yeah, if you want to see the rest of the series and that, yeah, NOVA, The Fabric of the Cosmos, look it up, and you can probably find links to it or whatever. But yeah, my link just doesn't work anymore because it got taken down for copyright reasons for whoever was putting it on the web. And here we go. I'm just going to turn my mic off.
So how did we discover them? These strange laws that seem to contradict much of what we thought we knew about the universe. Not long ago, we thought we had it pretty much figured out. The rules that govern how planets orbit the sun, how a ball arcs through the sky, how ripples move across the surface of a pond. These laws were all spelled out in a series of equations called classical mechanics, and they allowed us to predict the behavior of things with certainty. It all seemed to be making perfect sense. Until about 100 years ago, when scientists were struggling to explain some unusual properties of light. For example, the kind of light that glowed from gases when they were heated in a glass tube. When scientists observed this light through a prism, they saw something they'd never expected.
If you heated up some gas and looked at it through a prism, it formed lines. Not the continuous spectrum that you see projected by a piece of cut glass on your table, but very distinct lines.
It wouldn't give out a smeared kind of complete rainbow of light. It would give out sort of pencil beams of light at very specific colors.
And it was something of a mystery how to understand what was going on.
An explanation for the mysterious lines of color would come from a band of radical scientists who, at the beginning of the 20th century, were grappling with the fundamental nature of the physical world. And some of the most startling insights came from the mind of Niels Bohr, a physicist who loved to discuss new ideas over ping pong. Bohr was convinced that the solution to the mystery lay at the heart of matter, in the structure of the atom. He thought that atoms resembled tiny solar systems, with even tinier particles called electrons orbiting around a nucleus, much the way the planets orbit around the sun. But Bohr proposed that unlike the solar system, electrons could not move in just any orbit. Instead, only certain orbits were allowed.
And he had a really surprising and completely counter-physical idea, which was that there were definite states, fixed orbits that these electrons could have, and only those orbits.
Bohr said that when an atom was heated, its electrons would become agitated and leap from one fixed orbit to another. Each downward leap would emit energy in the form of light in very specific wavelengths. And that's why atoms produce very specific colors. This is where we get the phrase, quantum leap.
If it weren't for the quantum leap, you would have this smear of color coming out from an atom as it got excited or de-excited. But that's not what we see in the laboratory. You see very sharp reds and very sharp greens. It's the quantum leap that's the origin and the author of that sharp color.
What made the quantum leap so surprising was that the electron goes directly from here to there, seemingly without moving through the space in between. It was as if Mars suddenly popped from its own orbit out to Jupiter. Bohr argued that the quantum leap arises from a fundamental and fundamentally weird property of electrons and atoms, that their energy comes in discrete chunks that cannot be subdivided, specific minimum quantities called quanta. And that's why there are only discrete, specific orbits that electrons can occupy.
An electron had to be here or there and simply nowhere in between. And that's like nothing we experience in everyday life.
Think of your daily life. When you eat food, you think your food is quantized? Do you think that you have to take a certain amount of minimum food? Food is not quantized. But the energy of electrons in an atom are quantized. That is very mysterious, why that is.
As mysterious as it might be, the evidence quickly mounted showing that Bohr was right. Electrons followed a different set of rules than planets or ping pong balls.
My microphone's back on here. So timeline of things here, just for interest's sake here, Max Planck, in the 1900s or so, proposed that energy is emitted in discrete packets and so on, but didn't know why, right? Albert Einstein kicked it up a notch in 1905, photoelectric effect, saying it's particles and so on. Niels Bohr, after that, looking at the atom, proposed the idea of the fixed energy shells and so on, right? Electrons can only gain or lose specific amounts in atoms. And then, the relationship between things here, light is quantized as photons, Bohr, and there's electron energy levels and so on. The ideas are obviously pretty linked here, right? Electrons change energy levels by absorbing and emitting photons. The photon energy has to exactly match the energy difference between the levels and so on. Yeah, so Planck introduced quantization, essentially. Einstein applied it to, this was of energy in Planck, and then Einstein applied it to light itself and realized, oh, light's particles, right? And then Bohr applied it to matter with electrons and atoms, essentially, right? So leads to the foundation for quantum theory that we're going to talk about as we go. I liked how in the video it showed about how gravity and projectile motion, all that's all classical physics, right? Whereas the quantum electrodynamics and the Einstein's theory of general relativity and all those things, they have quantum, like the minimum bite-size pieces of energy in those fields built into them. So they're quantum theories. They get along with quantum mechanics. One question that could get asked about this, is the quantization of light really just due to the quantized nature of energy that electrons can absorb and emit from atoms? And because if you think of light is really just energy that's given off by electrons moving from one level to another in an electron. Like fundamentally, that's all light is, right? But it's not really just that simple, right? It's the quantization of light is not a consequence of the electrons having quantized energy level. Evidence shows light itself is intrinsically quantized. So obviously in the photoelectric effect, there was information that showed it's quantized, right? So yeah, don't think of this like maybe light only appears to be quantized because it can only exchange energy in chunks. It's not the case. Photoelectric effect we've talked about. Down here, light can behave as particles even without atoms involved. So there's another process called Compton scattering that beyond the course for now, at least anyways, where light can be shown to be transferring energy and momentum as if it were made of particles. And we're not talking about interacting with atoms at that point. Yeah, so in quantum physics, light is an excitation of the electromagnetic field, and then there's the other fields as well, right? The strong nuclear force field and so on. Yeah, quantization is built into the fields themselves, the field theories, so they're quantum field theories, as I mentioned. Yeah, so the correct relationship is that light is quantized, of course, it's particles, and electrons and atoms can only be absorbed in particular energy gaps. These are both true things, The atomic energy levels and photon energies have to match each other, but they're not caused by one another, right? So that is that. And I get that this is weird, wild stuff. Feel free to pause the video, slow it down, go back and see it again. What was that? I forget what was said about this and that. These questions are, for the most part, the big picture concept stuff, and then the one at the bottom here is, actually physically calculate the speed that an electron would get ejected off at. All right, so that is that. Thanks for watching.